A very good afternoon, dear students. Today we continue to statistical discrimination problems. First of all, we have the definition here. Statistical classification is a question of discriminating between the two populations under consideration on the basis of the measurements on various characteristics of the given individual. So any function of the measurements used to discriminate between the populations is called a discriminant function. Okay. Here, a not statistical classification problem is in fact the problem of finding discriminant functions which are best in some sense. When there are only two populations, the function ux x prime sigma inverse mu1 minus mu2 is a linear discriminant function for discriminating between the two populations np mu1 sigma and np mu2 sigma. Because in the last theorem we have seen that the function ux here is used to define the best classification rule when there are only two populations. So any function of x, where x is a vector of measurements on the individuals about which we are looking for a population to which it belongs, and ux is a function of this x prime, and ux gives a best classification rule, meaning it is used to classify the individual into one of the two populations. It can be considered as a discriminant function for discriminating between the two populations np mu1 sigma and np mu2 sigma. Discriminating means identifying the two populations differently. That is, population 1 is this and population 2 is this. If you know population 1, then you know the individual which population it belongs to. That means it is a classification. So classification means nothing but it is a discrimination between the two populations, and in particular if there are only two populations, discriminating between the two populations. So do not confuse with the two synonymous terms as classification problem and discrimination problem. We can think of a classification problem as a discrimination problem. When we think of a discrimination problem, any function ux is a linear discriminant function, where x is the vector of measurements made on the relevant characteristics of the individual. Okay, we'll continue. Now, Fisher's linear discriminant function, the definition is the linear function y is equal to x prime sigma inverse mu1 minus mu2 is called Fisher's linear discriminant function for discriminating between the two populations np mu1 sigma and np mu2 sigma. And further, the non-negative quantity delta square is mu1 minus mu2 prime sigma inverse mu1 minus mu2 is called Mahalanobis generalized distance. Mahalanobis generalized distance between the two populations. You note that in the red line, we know that variance of y is nothing but delta square. So you can compute the variance of y, that is Fisher's linear discriminant function, and you will see that it is nothing but delta square. One important point here to mention is that the generalized distance delta square here, the generalized distance delta square in some box, we have a coefficient here is 1 by p. This factor, namely 1 by p, is generally dropped for simplicity in the classification procedure in practice. It may further be noted that delta square so modified is the variance of the linear discriminant function due to Fisher. Okay, so we generally drop, suppose in some books you may find that here 1 by p coefficient here. But in the problem of the classification, generally we drop this. So we simply write this. So that is why we do not use this, and we only use mu1 minus mu2 sigma inverse mu1 minus mu2. Okay. So note that variance of y is delta square. Next, another definition is here, let gamma prime y be a linear discriminant function discriminating between two completely non-normal populations np mu1 sigma and np mu2 sigma. The quantity gamma prime mu1 minus mu2 whole square is, which is the square distance between the two means of gamma prime x under the two population is called the between variance. This is between variance of gamma prime x and the gamma prime sigma gamma. The common variance of gamma prime under the two population is referred to as its within variance. So this definition gives what is the between variance and what is the within variance. So this is the within variance and this is the between variance. Now a small theorem: of all linear discriminant functions discriminating between two completely non-normal populations np mu1 sigma and np mu2 sigma, the linear function y x prime sigma inverse mu1 minus mu2 has the maximum between variance, relative to the corresponding within variance. Okay. So this linear function is nothing but Fisher's linear discriminant function. Fisher's linear discriminant functions for discriminating between the two populations which are completely non-two populations. Okay. Now in the proof is very simple. We have the linear discriminant function gamma prime x, and we have to maximize gamma. We have to find gamma which maximizes the between variance relative to the corresponding within variance. That is to maximize this quantity delta square with respect to the components of y. Now since delta square is invariant under the change of scalar measurements of gamma, it is enough to maximize it subject to the condition gamma prime sigma gamma is equal to 1. So this is our normal procedure for maximization. Now introducing Lagrangian multiplier lambda and differentiating the function. So this is the between variance, and lambda is the Lagrangian multiplier, and this is the condition where the within variance minus 1 with respect to the components of lambda. We get the following system of maximizing equations. So this is our differential procedure for maximization. Ultimately what we get is this lambda gamma is equal to this, which means that gamma is proportional to, or gamma is a multiple of this quantity. You know that gamma is a multiple of this quantity, or you can say that gamma is proportional to this sigma inverse mu1 minus mu2. So for the purpose of discrimination without loss of generality, we can take gamma is equal to sigma inverse mu1 minus mu2. So the constant for proportionality here is 1. We can take for the purpose of discrimination. So that the best linear discriminant function is x prime gamma is equal to x prime sigma inverse mu1 minus mu2, which is nothing but Fisher's linear discriminant function. So this is the theorem, and we will continue 2 more theorems in the next video lecture. So as of today, let us have a good day.